Welcome to today's exciting journey into the world of hydrogen. Now, hydrogen may seem simple, but it shares some fascinating traits with its periodic neighbors. Let's start by talking about electronic configurations. Hydrogen, with its 1s superscript 1 configuration, is in the first position of the periodic table. Now, look at the alkali metals lithium, Li, sodium, Na, and potassium, K. They all have one valence electron too. Lithium has the configuration to 1, sodium to 8 1, and potassium to 8 8 1. Just like these alkali metals, hydrogen is electropositive, meaning it easily loses its single electron. In fact, hydrogen loses an electron and forms H, just like lithium forms Li and sodium forms Na. So, when it comes to oxidation, hydrogen behaves just like these alkali metals, showing a +1 oxidation state. Interesting, right? It's almost like hydrogen shares a kinship with the alkali metals despite its unique position. Let's now explore how hydrogen reacts, particularly when it interacts with nonmetals. Just like alkali metals, hydrogen forms compounds like water, HO, hydrogen sulfide, HS, and hydrogen chloride, HCl. Alkali metals like sodium also form similar compounds such as sodium oxide, now, sodium sulfide, NaS, and sodium chloride, NaCl. But here's the kicker. Both hydrogen and alkali metals act as strong reducing agents when they react with metal oxides. For example, when hydrogen reacts with copper 2 oxide CuO, it reduces the oxide to copper metal, forming water in the process. Similarly, sodium reacts with copper 2 oxide to form copper metal and sodium oxide now. So, hydrogen, just like its alkali metal cousins, is a powerful reducer in redox reactions. Now, let's shift gears and look at hydrogen's similarity to the halogens. Hydrogen has only one electron, making it just one electron away from achieving the noble gas configuration of helium 1s superscript 2. On the other hand, halogens like fluorine and chlorine, with configurations to 7 and 8 7 respectively, need one more electron to complete their octet. So, what do both hydrogen and halogens have in common? They both have a strong tendency to gain an electron. When hydrogen gains an electron, it forms H, and the halogens like fluorine and chlorine also form F and Cl, respectively. It's fascinating how hydrogen, despite being so small, shares these traits with the halogens, particularly in its electronegativity and tendency to form a 1 oxidation state. When we dive into bonding, hydrogen and halogens are quite alike too. Hydrogen forms electrovalent compounds like sodium hydride, Na, and covalent compounds like methane, CH, and water, HO. Halogens, on the other hand, also form ionic compounds like sodium chloride, NaCl, and covalent compounds like carbon tetrachloride, CCl, and methane, CH. Both hydrogen and halogens exist as diatomic molecules in their natural state H, F, and Cl. It's like they both enjoy being in pairs. As we see, hydrogen's atomicity, how it exists as a diatomic molecule, is similar to that of halogens, giving them a shared characteristic despite their differences in group and reactivity. Let's put hydrogen's reducing power to the test with a worked example. Consider the reaction of hydrogen with copper 2 oxide at standard temperature and pressure STP. The equation is simple CuO S plus Hg Cu S plus HOG. In this reaction, copper 2 oxide is the oxidizing agent and hydrogen acts as the reducing agent. As hydrogen gets oxidized to HO, the copper 2 ion Cu superscript 2 is reduced to copper metal Cu. The stoichiometry here is a 1:1 ratio, confirming that hydrogen reduces the copper 2 oxide to copper, much like an alkali metal would. So, when you're working with redox reactions, remember, hydrogen shows its reducing power just like the alkali metals. So, to sum it all up, hydrogen has a fascinating dual nature. Just like the alkali metals, hydrogen is electropositive, exhibits a +1 oxidation state, and acts as a strong reducing agent. But, on the flip side, hydrogen shares many characteristics with the halogens, such as electronegativity, the formation of diatomic molecules, and a 1 oxidation state. Whether it's forming ionic compounds or covalent bonds, hydrogen straddles the line between the s block and p block elements, making it a truly unique element. Understanding hydrogen's dual nature helps us see why it's classified as a group by itself in the periodic table. It's one of the most versatile elements we know.